Conventional engines, despite their complexity, used well-established manufacturing processes. Foundries knew how to cast engine blocks. Machine shops knew how to bore cylinders and grind valves. Supply chains existed. Tesla's turbine required starting from scratch. It required precision that only the most advanced facilities could achieve, and those facilities were expensive. At high rotational speeds and temperatures, metal behaves differently. Tesla's discs needed to be perfectly flat, no warping under centrifugal force, smooth, any roughness disrupted the boundary layer, heat-resistant, exposure to high-temperature steam or combustion gases, and durable, resistant to fatigue from constant high-speed rotation. The metallurgy of 1910 struggled with this combination. Modern materials like titanium alloys, advanced stainless steels, and ceramic composites didn't exist. Tesla's prototypes used available materials that worked, but not optimally. The turbine spun beautifully at 10,000 plus RPM. But in 1910, almost nothing else operated at those speeds. Industrial machinery, vehicles, generators, they all operated at much lower speeds. To use Tesla's turbine practically, you needed reduction gearing. But reduction gears added mechanical complexity, the thing the turbine eliminated, introduced friction and efficiency losses, required precision manufacturing themselves, and were expensive. The turbine's greatest strength, high speed, direct rotation, became a weakness in a world designed for slower, geared systems. By 1910, entire industries were built around conventional engines. Steam turbines, the bladed kind, were powering ships and power plants. Internal combustion engines were rapidly improving. Manufacturers had invested millions in tooling, training, and supply chains. Switching to Tesla's turbine meant retooling factories, retraining workers, developing new supply chains, convincing skeptical investors. Even if the turbine was better, the cost of switching was enormous. And in engineering, good enough and available now usually beats perfect but requires rebuilding everything. By 1910, Tesla was increasingly seen as brilliant but unreliable. His grand promises about wireless energy transmission had failed to materialize. His Wardenclyffe Tower was abandoned. He was involved in disputes over radio patents with Marconi. Investors were wary. When Tesla claimed 60% efficiency, they wondered if it was another overpromise. His previous financial backers had lost money. New investors were hard to find. Tesla's personality didn't help. He was uncompromising, dismissive of critics, and increasingly eccentric. He feuded with engineers who suggested modifications. He refused to compromise his vision for commercial viability. In 1914, World War I erupted, consuming Europe and eventually drawing in America. Industrial capacity pivoted to military production. Innovation in civilian technology slowed. By the time the war ended in 1918, the window of opportunity had closed. Conventional engines had been perfected under the pressure of war. Gasoline engines powered aircraft. Diesel engines powered submarines and ships. The infrastructure was entrenched. Tesla's turbine, still requiring refinement and investment, was forgotten. After World War I, Tesla continued working but his influence waned. He moved between cheaper hotels in Manhattan, unable to pay bills, living off a stipend from the Yugoslavian government and occasional engineering consulting.